Bismillahirrahmanirrahim. Okay, so next we will come to the third operating condition. In this operating condition, we have fixed RL or a fixed load resistance, but a variable input voltage. That is, this time the input voltage VI over here in figure 2.112, VI is now variable. So just at the first look, what should be the minimum value? What should be the minimum value of input voltage? From the first look of figure 2.112, the minimum value of the input voltage should be larger than the breakdown voltage of the Zener diode being used. Okay, so for the fixed values of RL in shown in figure 2.112, the input voltage VI must be sufficiently large to turn the Zener diode on. That is, we must ensure that the input voltage is sufficiently large to break down the Zener diode. The minimum turn on voltage I minimum is determined by load voltage is equal to Vz is equal to RL divided by Vi over RL plus R, and we arrange this equation to get input voltage minimum, that is Vi minimum is equal to RL plus R into Vz divided by R, equation 2.27. This is our minimum input voltage that we can apply. And then the maximum value of input is limited by Zener current IZM. Since IZM is equal to IR minus IL, therefore IR maximum is equal to IZM plus IL. What is this IZ? What is this IR maximum? IR maximum is the maximum current our series resistance can handle, or IR maximum is the maximum current that can pass through the series resistance R. So we are talking of this current, and here it is flowing, and here is flowing the IR maximum. Okay. Now, since IL is fixed at Vz divided by RL, why is IL fixed? IL is fixed because in the statement we have fixed RL and voltage, and in the circuit RL is fixed and voltage across RL is also fixed, that is Vz. Therefore, IL current flowing through RL, that is IL, it is also fixed. And IZM is the maximum value of IZ. The maximum input voltage is defined by VI maximum is equal to IR maximum into R plus Vz. So input maximum voltage is equal to the maximum current flowing through R multiplied by R value plus the Zener voltage. Equation number 2.29. So now let us come to example. Now let us come to example number. So now let us come to example number 2.28. The statement is determine the range of values of VI that will maintain the Zener diode of figure 2.121 in the on state. And let us look at the circuit diagram. This is figure 2.121. We have an input voltage VI. This range, the range of VI we have to determine. We have a series resistance R of 220 ohms. Current flowing through R is called IR. Then we are using a Zener diode of 20 volts, and the IZM, the maximum current that can pass through the Zener diode, is 60 milliampere, whereas the current flowing through the Zener diode is represented by IZ. Then we have a load resistance of 1.2 kilo ohms, and current flowing through the load resistance is called IL. We have to determine the range of input voltage that will maintain Zener diode in the on state. Now let us determine the minimum input voltage that we can apply. The minimum input voltage that we can apply for this circuit is equal to RL. The minimum voltage that we can apply as determined in equation 2.27 is equal to RL plus R multiplied by the Zener diode voltage divided by RL, and it is equal to 23.67 volts. And the current under such circumstances, and the current IL under such circumstances is 16.67 milliampere. The current IL under such circumstances is VL divided by RL is equal to VZ divided by RL is equal to 16.67 milliampere. And then for maximum current through IR, that is IR maximum, the maximum current that flows through IR over here, it is equal to IZ maximum plus IL. It is equal to 60 milliampere plus 16.67 milliampere, that is 76.67 milliampere. And then to find the maximum input voltage that we can use, we will use the IR maximum as determined in the last step. And the input voltage maximum is equal to IR maximum into R plus VZ. It is equal to 76.67 milliampere multiplied by 220 ohms plus 20 volt from the Zener diode. It is equal to 36.87 volt. So the range of voltage that we can apply for this circuit ranges from 23.67 volt to 36.87 volt. This is the range of voltage that will ensure that the diode is in on state, that is the Zener diode is in the on state, and we can use a resistance RL of 1.2 kilo ohms.
Excuse me, sir, what if the voltage exceeds 36.87 voltage level?
Yes, so what will happen? What will happen if our input voltage exceeds 36.87? So let us take input voltage equal to, let us say, 50 volts, correct? Now determine IR. Now determine IR. What is the value of IR? IR is equal to 50 volt minus 20 volt from Zener diode divided by 220 ohms value of R. This is equal to this is equal to 136 milliampere. Now, what is the Now 136 milliampere are flowing through this resistance R. ठीक है? Are flowing over here. Under such circumstances, what is the value of the load current? Load current is fixed at 20 volt from the Zener diode divided by 1.2 kilo ohms. We cannot change this value because they are fixed values. 20 volt from the Zener diode and 1.2 kilo ohm value of the RL itself. And this is equal to 16.67 milliampere. So we have found current in R, we have found current in the load current. Now what in the third step, what is the IZ, current in the Zener diode? This is equal to IR minus IL. ये सब फॉलो कर रहे हैं? मैं क्या कर रहा हूं?
Yes, sir.
Okay, so this is equal to 136 milliampere minus 16.6 milliampere. That is 136 minus
So
16.67. So this will be 119 milliampere. 119 milliampere. 119 milliampere is the current. 119 milliampere is the current that will flow through the Zener diode. However, the manufacturer has already claimed that the maximum current through the Zener diode should not exceed 60 milliampere. And whereas we are almost giving almost twice as the maximum current. So this is what will happen when we increase the input voltage larger than the calculated one. And as a result, our Zener diode, it will either in the extreme cases, it can be ruptured or it can be permanently be damaged.
But excessive current can beyond the limit specified by the manufacturer.
Yes, can you repeat your question?
But this means excess current can flow despite the limit given by manufacturer. It is not that
excess current excess current will only flow momentarily, and after that our diode will be permanently damaged.
So it's not like the current is limited to a specific value.
Which specific value are you referring to?
60 milliamperes. Because it is not like that how much we increase the current, it will only be remain 60 ampere. It can increase beyond 60 amperes or 60 milliamperes, sorry.
Of course, when we use a voltage of larger value, the current flowing through the Zener diode will exceed 60 milliampere.
So,
But this larger excess value will flow momentarily, and after that, the diode itself, it will be damaged permanently because we have passed too much current and too much power has been dissipated.
Okay, sir. So, but if you two Zener diodes in parallel with each other,
Two Zener diode can be a solution, but from statistics we know that two items can never be identical. So we might have slight changes across the two Zener diodes, and this slight change in voltage will create an imbalance, and we will have something called as the circulating current. So it's better to use a heavy Zener diode instead of two small Zener diodes in parallel.
Okay, sir.
ठीक है. So thank you very much, class. Please go through the examples, read the theory. Reading from the textbook is highly recommended, and solve the example that we have done today. Run them in in the simulation software also and confirm the results. ठीक है? Thank you very much. Assalamu alaikum.